Hey physics students, welcome to this video, and we may have a couple of them on work and machines. So let's see how far we get. All right, so an idea of a machine is that we need something to oftentimes help us do work. We talked about in the previous videos how work is a force which is a continuous force in a particular direction that provides movement in that direction. So there's often many things that we do where we need to make stuff move. So some of the most simple ones are like a car or a wheelbarrow, a bicycle. We'll go over a bicycle in one of these videos that I have right here. So what's the idea that's going on here with work and machines? Well, the idea is that with a machine, you put work in, and the machine outputs work. And it does this through several methods, and I'll go ahead and put up a couple of machines here so we sort of get an idea of how this works, right? And so when we look at a machine like this, this would be sort of like how a wheelbarrow works. If you notice, a wheelbarrow will have a wheel right here, and then there's a pivot point right here, and you lift up right here. So this is kind of like or another way we could look at this particular machine, this lever right here, would be like a bottle cap opener. So notice what happens is you put your input work here, and that's what FE stands for, exerted force, and that's going to be multiplied by the distance here. So we're going to have a force applied over a distance here. And then that, on the other side of this, is going to create another force over this distance. Now notice this distance here is a lot shorter. So what ends up happening is that this force has to be greater because these equal each other. So whatever force times distance I have on this side equals force times distance on that side. So that's how a bottle cap opener works. You have a big long distance of the bottle cap. You push down on this. It's a short distance here, and so the force is much greater. So we have this input work and output work. So oftentimes what machines do is they'll change the distance, change the length of the force applied so that a small force on one side comes out as a big force on the other. And sometimes what our machines will do is just change direction. So if you look here at this pulley, it's just a simple pulley right here. There's no amount of force really that's going to be helped here. So what's going to be happening is that when I pull this direction, okay, the pulley is going to pull back that direction, right? And so what happens is it basically just is a change of direction. Now, you start adding pulleys in here, and what's going to happen is that you pull a long distance here, and it's only going to end up hardly going up at all here. But that's the same thing I was talking about before, where we've changed the distance. We're going to have a big, huge distance, and then the work output's going to be a short distance, huge force. Some of the other things we do would be like a wedge like this. If you drive this into a chunk of wood, well, as you put your force down, it's going to exert force out on the sides, therefore splitting your wood. We use inclined planes, we use screws. All these things are machines that have an input work and an output work. And so what we would say with a machine is that the work out equals the work in, or the force that we put in times the distance we put in equals the force we get out times the distance we get out. Or we could rearrange that and say the force on the output of the machine divided by the force of the input of the machine equals the distance that we put in divided by the distance that we get out of the machine. And these two things right here actually have specific names. Okay, so when we're talking about the force of a machine, basically the ratio of the force that comes out over the force that we put in, that's what FE is force exerted, and this is force resisted, so on the other side. And we call this mechanical advantage. And so this is what we call MA or mechanical advantage. And so what's happening here is in mechanical advantage, if the force you put in is the same as the force you get out, the mechanical advantage is 1, because it would just be one thing divided by the same exact thing. Now, if the force you put in is a lot less than the force you get out, so then the mechanical advantage gets more. So let's say that the force you got out was 3, and you only had to put 1 in. You got a mechanical advantage of 3. So the higher the mechanical advantage, the less force you have to put into the machine, and the more it comes out the other side. Now, when we're comparing distances, we call that IMA, so ideal mechanical advantage. So these things are different in that mechanical advantage is a ratio of the forces, whereas ideal mechanical advantage is the ratio of the distances. Now, the idea of an ideal machine is important to understand. An ideal machine would suggest that all of the force we get in, or we put in, goes into coming out. The reality of a real machine is that it doesn't actually work that way. Real machines never produce complete, perfect efficiency. So we have these expressions for efficiency. So efficiency, we would say E equals the work out. So whatever output you get divided by the work in times 100. So the idea is that that these are not going to be equal, right? That this is not going to equal this because stuff happens. Stuff is lost as heat, and so on. And so the more efficient though we are, the more that whatever we put in is what comes out. And we try to develop machines that are as efficient as possible. So another way of expressing this is that workout. We talked about workout as FEDE. So we could say this. We could say that and we understand that workout divided by work in. We're just putting this over the top of this. And so another way of expressing efficiency is actually to say this, to say that efficiency equals the mechanical advantage divided by the ideal mechanical advantage times 100. So you can just take this divided by that, and that would equal 100. And so that essentially is the same thing as the work out divided by the work in. So it can be expressed both ways. So what we're going to do in the next video is I'm going to go ahead and go through an example of bicycle and sort of use all of these equations and show you how you can figure out the different kinds of things that are going on in a bicycle machine, which uses a lot of gears and wheels. So we call those wheel and axle is kind of the official name of the simple machine. So we have a lot of that going on in a bicycle. So in the next video, we're going to go ahead and analyze a bicycle and do a problem and kind of show you how these ideas of work going in versus work coming out, ideal mechanical advantage, and mechanical advantage works together in a machine called a bicycle.